We are entering an unprecedented time. Currently, there are nearly 3,000 operational satellites in orbit, and this number is only projected to exponentially increase over the coming years. Among these new satellites entering orbit will be one from RIT. In the next few years, the RIT Space Exploration Team will launch the Institute's first CubeSat. But before launching a CubeSat, universities like RIT need a method of communicating with and tracking their satellite. Satellite orbits are constantly changing, and orbital predictions can quickly become inaccurate. This can lead to communication failures or even a possibility of satellite collision. Currently, these collision probabilities are low, but as more and more satellites are entering orbit, it will be increasingly important for us to communicate with and track these satellites.
This is where multidisciplinary senior design project Localize Attribute Satellites in Orbit, or LASSO, comes into play. Our project aims to create a ground station network that will be able to autonomously track satellites and update their orbits. LASSO is centered at 437 MHz, which is a common band used by CubeSats and other amateur satellites. The LASSO network will have 3 ground stations that are located to form an equilateral triangular plane. As the satellite passes over this plane, its signal will arrive at each of the stations at a different time due to varying distances between the stations and the satellite. By knowing these differences, we can triangulate the position of the satellite and determine its orbital parameters using a method known as time difference of arrival.
We believe that this project has an opportunity to be used not only by RIT, but by other universities or hobbyists across the world. Other satellite tracking methods are expensive or infeasible, particularly for some academic institutions. Project LASSO offers a solution at a reasonable price that will also provide new research and educational opportunities.
Project LASSO is designed exclusively using over-the-counter parts, which allows for the system to be standardized and widely adopted. Our system will use a QFH antenna to receive signals in the 437 MHz range due to its wide field of view and relatively small design. The Joey box will be a small and weatherproof box that will be placed outside near the antenna. Inside the box is a lightning arrestor, which will protect the system from lightning strikes, as well as a low noise amplifier to increase the signal to noise ratio of the signal received at the hopper box. The Joey box is separate from the rest of the electronics, as we need the low noise amplifier to be as close to the antenna as possible to minimize the amount of noise added to the signal before amplification. The other electronics will be housed in a steel hopper box that has been environmentally tested. Environmental reliability is a requirement, as some sites may require this box to be outdoors. We're using the HackRF1 as our software-defined radio. This is needed to capture and record radio signals from our QFH antenna, which are then sent to the Raspberry Pi. The Raspberry Pi acts as a main control unit for the system and interfaces with the HackRF1, the GPS hat, as well as the network to both send and receive data and commands to our main central server at the RIT campus. All of the electronics in the hopper box are connected to a combination surge protector and UPS. This will protect the system from any fluctuations on the power grid and can also provide backup power during quick outages. The GPS antenna hat sits atop the Raspberry Pi and is connected to an antenna that allows us to locate the stations as well as receive the current time, which is needed to synchronize the 3 base stations.
Pictured here is one of our 3 ground stations that is located at the Mies Observatory. For this site, we were able to mount our QFH antenna at the top of a 40-foot utility pole. The Joy box is then located at the bottom of that utility pole. We then ran a coaxial cable underground from the utility pole into the observatory, where we housed our hopper box and other electrical components. Our GPS antenna is then mounted on top of the observatory.
Project LASSO utilizes a Ubuntu server in conjunction with Raspberry Pis in order to capture satellite signals using GNU Radio. The user will log into the server and input the desired frequency using a GUI. The server will then send out a request for all the ground stations to capture that frequency. When done capturing, the pies will send the captured data back to the server for processing. After processing, the server will determine the satellite's location using cross-correlation and TDOA equations.
Project LASSO officially began in 2019 under last year's MSD team. This year's iteration of Project LASSO is extremely grateful to help realize the original vision for the project and build upon the outstanding accomplishments set by last year's team. We would like to especially thank Anthony Iannuzzi and Andrew DeVries for taking the time out of their schedules to continue supporting the project this year. We would like to thank our project guide, Martin Pep, for his ongoing mentorship and dedicated support for this project. Thank you to James Stefano for his ongoing support, subject matter expertise, and helping to connect us to our different site locations, as well as Russell Jost for his expertise and support. Lastly, we would like to thank our project sponsor, L3 Harris, for graciously donating $5,000 towards our project budget, and Dan Harris from L3 Harris for his subject matter expertise and presence at our team's review meetings.